All right, thanks everybody. Yeah, so let's see. So I'm going to talk to you guys today about the architecture inside of a rack scale, Helios system, and specifically the GPU architecture, which is my area of specialization. And just to kind of get us going here, I want to talk about like where we're coming from and where we're headed to. Obviously, in the past decade of AI infrastructure has really been, about increasing compute capabilities, both within the GPU and in the system architecture. And the solutions, yesterday's solutions as shown here, really an extension of high-performance computing architecture in terms of building an accelerated node and then scaling that through cluster networking. And then today's solution, as you saw, Lisa talking about earlier, is obviously it's different with these rack scale architectures. And so from a GPU perspective, what really matters today is not just optimizing compute and memory, but really doing system level optimization through very specific co-design for the workloads that are going to be running on these systems. And so AMD's solution that you guys saw a lot about this morning is obviously Helios. And like I mentioned, like what I want to talk about is the engine inside, or the GPU engine inside of Helios specifically, which is the MI455X GPU. So in order to give us the most time possible, I want to kind of skip forward into the GPU here, and I'm going to go through a lot of the details on how we organized the GPU, how we built it, but also some of the detailed features on one of the things that is most important to me is delivering application performance to the programmers, and also making it easier for programmers to extract performance out of the GPU closer to the roofline, right? And that's really been the focus for us in this generation, not just driving top line speeds and feeds, okay? But before we can talk about those features, you need to kind of understand the organization of the chip. And so that's what this slide is all about. And I just want to go through that really quickly, just so we all have a foundation to stand on. And I've got some other slides on the memory architecture, and I'll go deeper into that in a little bit. But fundamentally, it's a chiplet architecture. Lisa mentioned in her keynote, there's 12 chiplets, and they're outlined here. So these chiplets here, XCD, there's 4 of these per what we call fabric cache dies. So these are the fabric cache dies here. This is a 3D structure. So these XCD chiplets sit on top of these FCD chiplets. And then the FCD chiplets are connected together in a 2.5D package so that they can communicate and we can access all the memory globally across the two. So each of these FCDs has 6 of these HBM4 sites, and together they bring together the 12 HBM4 stacks of memory that we talked about in the keynote earlier, and also 8 of these XCD chiplets. And you can see within each of these chiplets we have 2 shader engines, and these shader engines are what hold the workgroup processors that are the fundamental building block of the CDNA5 architecture, which is what we're going to talk about. In addition to these core chips, I do want to mention one other thing, and I'll go into this in the cache and memory system in a little bit, but we've reorganized our cache hierarchy in CDNA5, and what was an L2 cache in the XCD in the previous generations has now been removed and repartitioned from the XCD chiplet into the FCD. And in the previous generation, we had a 3rd layer cache, which we call the infinity cache, but that layer has been flattened out, and so now we just have the L2 cache backing these SEs. So in previous generations where we only had the L2 cache backing the shader engines that were in one of the XCD chiplets, now that L2 cache is backing all of the shader engines on one FCD. So that's one of the key differences between the previous generation and this generation. And again, I'll get a little bit deeper into that, but I just wanted to call that out. And then we've also separated out the I/O subsystem. So now the I/O subsystem is on these 2 chips on the side. Still refer to those as an I/O die. And this is how we connect into the system, the rest of the system architecture, both for our interfaces into the EPIC host, which we use our Infinity Fabric for, but also how we connect up to the scale up and the scale out networks, right? So we have one of these that's specifically implemented for our scale up interfaces. If you've had a chance to go to one of the other talks related to that, that's our UA link over Ethernet, which gives us the 72 lanes at 200 gig to connect up to the rest of the GPUs in the pod or in the scale-up domain. And then in addition to that, we have another set of interfaces on the other side of the chip that allow us to connect multiple pods together to form clusters using the scale-out networking, okay? So hopefully that gives you a little bit of a grounding on the overall organization of the chip. So I want to click a little deeper now into a couple of key areas that we've focused our innovation on. And those come down to the compute and the memory, and then, like I said, extracting efficiency out of those systems for delivered workload performance. So let's start with the compute. So there's some pretty big changes in this generation relative to CDNA 4. We've completely reworked the compute core. Previously, based off of our GCN architecture, we referred to the core as a compute unit. In this generation, this is now referred to as a workgroup processor. The organization of the SIMDs is different. Previously, we had 4 SIMD 16s or 16-lane SIMDs within the compute unit. We've replaced that now with 4 32-lane SIMDs, and instead of running wave 64, so 64-thread waves, we're now native on wave 32, so 32-lane waves. And this is, this is good for the programmer because it reduces register pressure, reduces branch divergence penalties, and also instruction latency because we're actually issuing 32-thread ops on 32-lane SIMDs, and so we can dispatch those in one cycle, and so we can get a new op dispatched every cycle. All right, and so what that makes it easier to do is to do fine-grained interleaving of your operations versus before where we had 64 threads that had to dispatch across 4 cycles on a 16-lane SIMD, right? So it's a little easier to get fine-grained workload efficiency because of this change. So that's one of the reasons we did that. We have some changes to our block scale formats. I've got another slide on that I'll talk about in a minute. We have some new data conversion formats or operators that I'll talk about a little bit too. But in addition to those, we've increased our transcendental operations. We've added a new op for TANH. We also increased throughput on those because we need to scale those in line with the tensor throughputs that we've done. So we've got some pretty significant tensor throughput increases per core. We have 256 workgroup processors per GPU. That's the same number of compute units that we had on MI355. So the number of cores, if you will, is the same. So when you see the throughput increases, that is a per core throughput in line with the what we show as the top level throughputs. So these numbers that are over on the right in gold are really the tensor core per numerical format rate increases for the workgroup processor relative to the compute unit on MI355. In addition to the transcendental operations, we've also scaled up the vector operations because for attention, you need all of them to work together. We still are building a very balanced machine, as Lisa mentioned. Our intent with Instinct is that for training and for inferencing, that it can run both, the full training workload and also prefill and decode very efficiently. So we have very high levels of tensor core performance for large matrix multiplication in prefill, but also for decode, we've got the bandwidth in there to be able to supply the tensors and vector operations to keep up those in the transcendentals as well for the softmax and layer normalization operations, right? You've got to balance all that together and strong scale everything, and so that's what we've done. Okay, on the numerical formats, just a quick breakdown on those. It's the same basic formats that we had in MI355, couple changes. As Lisa or Dan or somebody mentioned, in addition to MI455, we have another variant of MI400 series called MI430. And so what we've done in this generation is we have heavily weighted MI455 towards AI performance. And then we have another variant that, leveraging our chiplet architecture, replaces the XCD chiplet that I showed earlier with one that's built for traditional simulation. Lots of double precision floating point in that other variant. And in this variant, we still continue to carry double precision floating point, but it's there for software compatibility. So the rates are significantly reduced. And we use that area to increase AI performance across the board, right? So that's the change up at the top for Float 64. Also in the AI formats, you can see here, we still carry MXFP 8, 6, and 4, but we've added block 16 in addition to block 32. So that's new for MI455. And on MXFP4, we have new fractional scaling, which is shown here. So we support E8 M0, E5 M3, and E4 M3, right? And those are unsigned and then signed, right? And so we can use those to reduce quantization error as we go through that step in these block formats. And that what the main workload benefit of that is you're able to do things with FP4 that you couldn't do in the previous generation in terms of convergence, right? So this is a really important new feature. Also mentioned up here at the bottom of the slide that we have these 4-bit tensor formats that allow us to store in, through an additional quantization step. You can take these MXFP formats, compress them into using these lookup table instructions, and store those in memory for additional compression, and then dequantize those before you compute with those back into the MXFP formats. So it's a flexible set of instructions that allow you to do that, and that's fully programmable, and we'll have that all published in our ISA specification, which is going to be coming out in the next few days. So I want to talk a little bit about the organization of the cache and memory system. So these diagrams, this is MI355 here on the left, and each of these dashed outlines, it represents a different level within the GPU. So I know it's hard to read, but this says, GPU private, GL2, SE, CU, and then SIMD. And then similarly over here, this is the GPU and GL2, and then the XCD, and the shader engine, and the workgroup processor, and then finally the SIMD. So these are the different levels of hierarchy within the cache and memory system, if you will. And the numbers that are written up here are the number of those that exist in the GPU, right? So we have at the GPU level, of course it's 1, and then the GL2, in the case of MI355, we had 8 of them, whereas in MI400, we have the GPU private, of course, 1, and then GL2, there's 2. Right, so there's been a good bit of reorganization in the cache architecture as a result of these changes. And the reason, before I get into the details of the what, the reason we did this is because we wanted to significantly increase a few different parameters. Right, one of them is that there's some cases where, as we move between kernels, we needed to make some writes in the L2 cache in MI300 series globally visible. And so we had to take the time to do some cache flushes. So that had an impact on kernel-to-kernel latency. And so we wanted to remove that in MI400 series. And so what we wanted to do is then have an L2 cache that more of the shader engines work collaboratively within. Right? So that was one of the changes. We also wanted to increase the throughput of global atomics. And so we wanted to move the atomic units back into the L2. Versus on MI300 series, the atomics were in the Infinity Fabric. And so that was another reason. And then thirdly, we just wanted to increase the global bandwidth of the L2 cache. And so all of these things drove us to a design point that's different in that the L2 cache was moved from those XCD chiplets into the fabric die that I mentioned earlier. So the result of that is that we now have these two large L2 caches, right? So each one of them is 96 megabytes. So in aggregate at the GPU level, it's 192 megabytes. Versus the organization in MI300, we had this single 256 megabyte cache that was shared across all the L2 caches, each of the L2 caches being 4 megabytes, and there were 8 of those, right? So that's the key cache hierarchy and organization change. And the result of this is that each of these L2 caches independently can deliver 1.5 times the bandwidth of the aggregate bandwidth of the Infinity cache in MI355. Then what we do on the Infinity Fabric side is we maintain cache coherency, hardware enabled, of these two L2 caches so that you don't have to worry about that as a programmer, right? So we still can present the entire GPU as a single device. You know, we call it SPX mode, or single partition accelerator. You can still use all of these resources together, and the hardware will manage the coherency between the two. Same thing for global atomics. So if you're doing device scope atomics, and SPX mode, the atomic units in the two L2 caches are able to coordinate with each other, and we have the mechanisms to run them at a very high rate while exchanging those cache lines periodically for data sharing. So that from a software point of view, it just looks like a device scope atomic, and you can't tell exactly what's going on, and the hardware is managing that to give you a much higher performance than we had before. We still have atomic units in the Infinity Fabric. We use those for system scope atomics. So if you want to execute atomics at system scope, we can still do that, and we execute those back in the Infinity Fabric like before. So that throughput helps with all sorts of synchronization, and getting that done in a much faster way relative to what we had before. Okay? There's a couple other key things that I just want to point out. We have these broadcast arbiters. So when we bring tensors in, there's a lot of data sharing opportunity for the work groups that are involved in executing the tensors for matrix multiplication. And these broadcast arbiters allow us to distribute the reused tensor data between multiple workgroup processors without having to refetch that data over and over again. So that's a power savings and bandwidth amplification. And then finally, we've greatly increased the size of the LDS, so the local data share. That's up to 320 kilobytes now. And then we have a 64 kilobyte L1 cache inside for the vector data cache. Okay, so quite a number of changes. And then this is just showing the bandwidth relative to MI355 that we extract out of those resources. Okay, so getting short on time, so I just want to talk about a few features for efficiency. We now have clusters, which is a new concept that allows you to, as a programmer, collaborate between multiple work groups. So think of it as a concept above work groups, so you can group work groups together, form clusters. This gives you additional controls over work placement and data sharing. So that's a new thing. We also have some new synchronization primitives for split and name barriers, which is a nice way to get additional performance. So that if you have a producer-consumer, once the producer signals that it's done its side before the consumer consumes the result of that, the producer can go ahead and start working on something else. So that's what the split barriers are. And then the name barriers also allow you to not have all work groups try to synchronize together. You can have certain work groups synchronize on a certain barrier, and others can move on, right? So these are the reasons we did those. We also have new prefetchers that allow software to pipeline and hide instruction fetch and data latency. And then significant changes to the front end of the GPU for kernel dispatch and launch latency improvements. So all of these things together allow us to get a lot more efficiency out of pipelining and using the resources in some new and asynchronous ways that we weren't able to do in the previous generation. Okay, and then the last thing I'll just mention is we have a new architecture for our SDMA. I don't have time to go into a lot of details on this, but it's something you can read more about in the white paper. But the key benefit here is we've made it easier for programmers to use the SDMA resources, and we actually take care of mapping that out in the most efficient way to the physical memory layout within the GPU and to the links that are used for communicating within the scale-up domain of Helios. So really excited about this new architecture. I hope it helps programmers make better use of the DMA engines instead of using workgroup processors for communication. So I think that'll be very useful. Okay, so with that, I'll wrap up and just say, we've tried to work across all of these domains, co-designing not just hardware and software, but at the system level, and also with all of the latest technologies that we can deploy to bring the best user experience to our GPUs, to the applications world. So I hope you enjoy using MI400 as much as we enjoyed building it for you. So I'll stop there.